In this video, I'll introduce the adjacency matrix of a graph. We'll look at an example. We'll prove Theorem 2.2, which relates powers of the adjacency matrix to the number of walks of length k between two vertices. And finally, we'll look at an example of applying that theorem. So that is to be able to multiply matrices without actually having to multiply them by using structures of the graph. So first off, the adjacency matrix of a graph is a 0, 1 matrix. So every entry is either 0 or 1. So typically we denote a matrix with brackets, Aij. So it's, adjacency matrix is this matrix where, so how do I define the entries? Aij is equal to 0 if vertex I is not adjacent to vertex j, so that is if ui, uj is not in the edge set, and 1 if ui, uj is in the edge set of the graph. So that is, we create a matrix that that stores the edges of the graph, is one way to think about this. So okay, so here's a graph. Let's look at an example. Let's build the adjacency matrix of this graph. So for every row, or for every vertex of the graph, I have a row and I have a column. So one thing I'll do is I'll just note, yeah, like row 1, so v1, v2, v3, v4, v5, and I also have one for each column, v1, v2, v3, v4, v5. And now I'm going to build this matrix. So I'm just labeling my rows and columns here. Typically we don't label the rows and columns, but we just keep in mind that vertex 1 is the first row and the first column, and so on. So since every vertex is not adjacent to itself, right? No vertex can be adjacent to itself in a graph. There's no edge between a vertex and itself. The diagonals of this matrix are 0. And then I'll fill out the rest of this. I'll put a 1 if that vertex is adjacent to the other vertex, and a 0 if they're not. So for instance, v1, v2, there's an edge between v1, v2 is an edge. So that means v1, v2, I get an edge here, and v2, v1, I also get an edge. So in particular, this is going to be a symmetric matrix. v3, v2 is an edge, so v2, v3, I put a 1 there. v2, v3, I put a 1 there. Let's see, v3, v1 is not an edge, so 0 there and 0 there. And we just continue like this. v3, v4 is an edge, so I put a 1 there, 1 there. v2, v4 is an edge, so 1 there, 1 there. v1, v4 is not an edge, so 0, 0. And then finally, v5 here is an isolated vertex, right? It's not adjacent to anything, and so all of its entries will be 0 in both the row and the column. So I get this matrix. And like I said, we typically don't label these. We just keep it like this, and this gives us the adjacency matrix of the graph. So great. So this kind of stores, right, like I said, this stores the adjacencies of the graph. Now, the first big result to come out of this is looking at powers of this matrix. So multiplying this matrix by itself k times and looking at what that gives us. In particular, we get Theorem 2.2. So if we have a graph with this vertex set, v1 up through vn, like we had there, v1 through v5, then if I raise this matrix to the kth power, the ij entry of it is the number of vi, vj walks of length k in the graph. So this is pretty cool. So if I raise the adjacency matrix to, say, the third power, and I look at, say, the 1, 3 entry, so 1, 3 entry, that would tell me the number of walks of length 3 between vertex 1 and vertex 3. So this is the idea. Let's take a look at a proof. I'm going to write proof sketch here because I don't want to write every single last detail. So I'll just say proof sketch. Oh, so yeah, before we do that, we have to talk about what does it mean. Here I say the number of different VIJV walks. So what makes a VIVJ walk different? Well, we'll just assume we'll define two walks to be different if they don't contain exactly the same vertices in the same order. So that's all we mean by different here. And then also, before we do that, we want to use some notation. So this can get a little bit messy. We'll use some notation here. I'll let A, I, J with a little superscript in parentheses to be the IJ entry of the kth power of the matrix of AK for any positive integer K. So how do I prove something like this? This seems like a tough thing to prove. It really comes down to what the definition of matrix multiplication is, how matrix multiplication works. And then, since I want to do this for every positive integer K, it seems like induction is the right idea for this. So we're going to proceed by induction. So first we'll consider the smallest positive integer K, that is K equal to 1. So if K equals 1, then Aij 1, so which is just Aij, right? So the ij entry of A, big A, is equal to 0 if Vi Vj is an edge, is not an edge, and 1 if Vi Vj is an edge of the graph. Right, that's just our definition of adjacency matrix. So how does that relate to this theorem? Well, what is a VI-VJ walk of length 1? So I'll say a VI-VJ walk of length 1, so it's just length 1, that means there's just one edge in the walk. And so it must just be that edge between Vi and Vj. Length 1 is just an edge between Vi and Vj. So that is, it's exactly this matrix, right? There's a Vi Vj walk of length 1, if and only if, or I guess I'll say there's exactly one Vi Vj walk of length 1, if and only if there's an edge between Vi and Vj, which gives us exactly just the adjacency matrix for the graph, that is A to the first power. And so I'll just, that case is pretty easy once you realize what a Vj walk is of length 1. It's just an edge. So assume for some positive integer K that Aij, the ij entry of the matrix A to the K gives the number of Vi Vj walks of length K. So there's our induction hypothesis. And now we're going to show that the ij entry of, so Aij to the K plus 1 is the number of Vi Vj walks of length K plus 1. So I'll say notice A to the K plus 1 is equal to A to the K times A. So we would obtain A to the K plus 1 by taking A to the K, which by our induction hypothesis contains the number of Vj walks of length K between any two vertices. Take that and multiply it by the adjacency matrix again. So I'll also say, notice that any vi, vj walk of length k plus 1 is obtained from a vi, vt walk of length k, where vt is adjacent to vk. So that is, I get a walk of length k plus 1 between vi, vj. One way to do that is to look at all of the vi, vt walks of length k, where vt is some vertex adjacent to vk. And then adding that edge between vt and vk will give me a walk of length k plus 1. Okay. So where do we go from here? Well, again, it comes down to matrix multiplication. So a to the k plus 1 is a to the k times a. A to the k is going to give me the number of vi, vj walks of length k. But in particular, so yeah, let's look at the ij entry of a to the k plus 1. So how is that obtained by matrix multiplication? Well, aij, that entry, k plus 1, is equal to, right, I would take the row I of a to the k and multiply that by, or take the inner product, rather, of that row with the j column of a. So what does that look like? That looks like ai1 in a to the k times a1j plus ai2 a2j in a to the k, and so on, right? Row I times column j is what I'm doing here. Rather, it's the inner product between the row and the column, but it's fine to think about it like this. In of the kth power of the matrix times a and j. So in other words, this is the sum from t equals 1 to n of ait to the k times a tj. Right, row I times column j. Add them all up, and that gives us the ij entry of a to the k plus 1. So now, what's the thing to notice? Again, I want to keep this in mind that every vi, vj walk of length k plus 1 is obtained from a vi, vj walk of length, or a vi, vt walk of length k, where vt is adjacent to vk. So I want to pay attention to these. So these are just coming from the adjacency matrix, right? There's no superscript here, so these are just the adjacency matrix. So maybe it's easiest to think about this in the general case. So maybe written over here. So think about what each of these terms is. So this term AIT, the IT entry of a to the k. So this is telling me by induction this is the number of VI, VT walks of length k. And then this ATJ, this is 0. Sorry, I was getting cut off. 0 if VT, VJ is not an edge, and 1 if VT, VJ is an edge. So that is, I'm going to look at right. We have one for each entry, each vertex of the graph. Now the vertices that are not adjacent to Vj, this term is going to be 0. So maybe V1 is not adjacent to Vj. Then this would be 0, and this whole entry would just go to 0. Right? So that is, even though there may have been a bunch of walks between Vi and V1, well, I don't care. Those aren't going to give me any walks between Vi and Vj because those walks don't end at a vertex that's adjacent to Vj. But maybe this one is, maybe a 2j, maybe V2 is adjacent to Vj. Maybe this is a 1, in which case I'll do 1 times this, which is the number of Vi V2 walks of length k. So look at what this is counting when I sum all these up. So I'm only gonna get a term for each vertex that's adjacent to Vj, and the term is equal to the number of Vi Vt walks of length k. And so for each of those, then I just take that extra edge from Vt to Vj, and that gives me a Vi Vj walk of length k plus 1, because I now have that extra edge. So right, that's, I mean, a little bit hand wavy for you, but hopefully you get the idea. If you want to look at the nitty gritty of this, definitely read through this carefully in the text. But this is essentially what's going on. I'm counting the number of k plus 1 Vi Vj walks of length k plus 1 by multiplying a to the k times a. I think I'm going to leave it. There. But this is what's going on. It comes down to matrix multiplication and how to obtain walks of length k plus 1. Maybe I'll write a little bit more to try and make this clear. So this sum gives the number of Vi Vj walks of length k is the idea. Okay, so let's look at an example of this. So here I have this graph, graph of order 4. Let's go ahead and find its adjacency matrix. So let's see. So 0, 0, 0, 0, right? It'll be a 4 by 4 matrix. V1's adjacent to V2, so 1, 1. V1's adjacent to V3, so 1, 1. V1 is not adjacent to V4, so 0, 0. V2 is adjacent to V3, so that's a 1, 1. Let's see, V2 is not adjacent to V4, so 0, 0. And then finally, V3 is adjacent to V4, so 1, 1. And there's my matrix A. So there's the adjacency matrix of this graph. By the way, we also sometimes use the notation, if it's not clear from the context, maybe if there's more than one graph going on, A of G, like that. And then, so now if I square this matrix, and I urge you go ahead if you have a calculator on you, or you can do matrix multiplication in your head, or bring up Wolfram, something like that. You can put this matrix in and raise it to various powers, and it'll tell you how many walks of each length there are between any two vertices. So what's cool with this theorem is I can actually do matrix multiplication by just looking at the graph, by looking at the number of walks. So, right, you can use it both ways. If, say, I have a very big graph and I want to know the number of walks between two vertices, well, I'll put that matrix into a computer and raise it to the whatever power I want to consider, and then I'll have a matrix of the number of walks between any two vertices. But alternatively, for small things, and to sort of test you on if you're understanding this theorem, we can compute small powers of A by just counting numbers of walks between two vertices. So for instance, A2, this is the number of walks of length 2 if I'm looking at the 1, 1 entry from V1 to V1. So that's the number of walks of length 2 from V1 to V1. So let's see, how do you obtain a walk of length 2, a closed walk of length 2 from V1 to V1? Well, you have to go out to a vertex it's adjacent to, and then come right back, right? You can only use 2 edges. And so actually, in general, this is giving me the degree of each vertex, right? There's 2 walks of length 2 between V1 and V1. One that goes to V3 back to V1, and one that goes to V2 and back to V1, and that's all of them. V2, again, we just have 2 walks. For V3, V3, we have, let's see, 1, 2, 1, 2, 1, 2. Again, in general, it's the degree of each vertex. And 1. But that's just along the diagonal. For the other ones, I have to think about it a little bit. So, right, how do I get a V1, V2 walk of length 2? Well, 1, 2, there's 1, and it looks like that's the only option I have. So that's just 1. And again, this is symmetric, right? If there's 1 V1, V2 walk, then there's only 1 V2, V1 walk. So let's see. So now here's the 3, 1. So how many walks are there between V3 and V1 of length 2? Again, there's just 1. And we go through and just keep recording the number of walks. So V1, V4 walks of length 2, 1, 2. There's just one of them. So 1 there. This would be the number of V3, V2 walks. Oh, I can copy these down because I know it's symmetric. And let's see. There's 1 V3, V2 walk of length 2. 1 there. V2, V4, V4, V2, either way. Or V2, let's see, yep, just one of those. So 1, 1. And then finally, this would be the number of, let's see, V4, V3 walks of length 2. Oh, there are none. So 0, 0. Now, another interesting thing, let's do one more. Let's look at A cubed, the third power of the adjacency matrix. So the ij entry of this is the number of vi, vj walks of length 3. And again, I want to pay particular attention to the diagonal here. So think about how many walks of length 3 are there between, say, V1 and V1. So here's one as I go to V2, V3, and then back to V1. 1, 2, 3. That's a walk of length 3. I could also go the other direction. V1, V3, V3, V2, V2, V1. And so in this case, and in fact in all cases, the diagonals of this, I get 1 for each, or I get 2 walks of length 3 for each triangle that this vertex is a part of. Right? So this will be 2. There were 2 walks of length 3, one going this way around the triangle, one going that way around the triangle. And that's all of them. And this is the same for each of these. V2. This should also be 2. This should also be 2. So in general, the I, or the, let's say, KK entry of A cubed is twice the number of triangles that contain the vertex VK. In particular, V4 here isn't a member of any triangle, and you'll notice there's no walks of length 3, no closed walks of length 3 beginning and ending at V4. So this is 0. For these other entries, we can just count. So this would be V2, V1. How many walks of length 3 are there? Let's see. 1, 2, 3. No, that's not going to work. 1, 2, 3. There's 1. Let's see, what else? Right? V2, V1 walks. So I count 1, 2, 3. I could also go 1, 2, 3. That's another one. Let's see. There should be one more that I'm missing here. Let me indicate these in blue. 1, 2, 3. There's 1. I could also go 1, 2, 3. There's another walk. What's the one I'm missing? 1, 2, 3. No, I can't do that. Oh, I'm missing one of these. Let me think for a second. I found the one I was missing. How about this one? V2 to V1, V1 to V3, and then V3 back to V1. And that's all 3 of them. And we can fill, and again, it's symmetric, so there'd be a 3 here. And then what about the paths, the walks of length 3 between V3 and V1? Let's take a look at those. 1, 2, 3. There's 1. 1, 2, 3. There's 2. 1, 2, 3. There's 3. And then there's one other one I'm missing again. Did I get that one? Yeah, there should be 4 of these. 4. And I'll just fill out the rest of this. So I'll let you verify that these are indeed the correct entries. And in fact, right, we can do this in 2 ways. So we could just compute a cubed, or we could go through and find all the different walks. In particular, V1, V4, there should only be one V4 walk of length 3, right? And that would be 1, 2, 3 is the only way to do that. So that's the idea. That's using theorem, Theorem 2.2, to compute adjacency matrix, powers of adjacency matrix. Okay, that's it for this video. Sorry, that one was a little bit long.